Hello, everybody, and thanks for joining my talk today about optical depth in dust rings. As you all know, since the era of high-resolution images of protoplanetary disks, we know that these disks show substructure in the dust emission. And this can be rings, it can be spirals, can be vortices, and they seem to be everywhere. And also Kees looked in his DSHARP 6 paper a couple of years ago into close detail of 8 rings in 5 of these disks and tried to investigate, where do they come from? Because one of the assumptions is that rings are trapped in pressure bumps because dust particles, they just follow pressure gradients, and if you have a pressure bump, they are just collected towards the center of the pressure bump. And so he was looking into details of 8 of these rings. And what he was doing was he was fitting Gaussian intensity profiles onto those rings. And so he could extract the width of these rings. And by subtracting the beam size, he could also extract what is about the dust width of these rings. And basically the result can be summarized in this plot where you see data points for all of these 8 rings that he was looking to. And first of all, the green line that you see in here is the beam size. And the blue dots are these widths that are extracted just from fitting Gaussians. And as you can see, all of the widths are larger than the beam size. So good news is all of these rings are resolved. Then another idea was, okay, if there are pressure bumps in the gas that are collecting these dust particles, that means the minimum size one of these pressure bumps can have is the pressure scale height, because otherwise it would not be a stable configuration. So what he then also was plotting here in orange is the pressure scale height at these locations. And as you see, 5 of these rings are below, widths of these rings are below the pressure scale height, meaning that those are signs, or that indicates that the dust particles are trapped in pressure bumps. So they were drifting into the center of this bump, and they have to be smaller than the pressure bump thickness, width. And for these 3 other rings that you see here, it cannot be excluded. It's just the widths are larger than the pressure scale height, but the pressure scale height is only a minimum of the gas pressure bump that can be there. So this is one major result, that, okay, we actually see there are dust particles trapped in pressure bumps. And the second major result is, if you look at all these rings and you extract the optical depth, they seem to be roughly all around the same number. And not only from the DSHARP sample, which are the purple disks, but there are also other publications like Macias et al. They also looked at the optical depth of these rings, and they are all in the same range. So it's definitely below 1, and they are somewhere between 0.2, 0.5. And this is super weird, because why should this be? All of these disks are at different ages, they have different sizes, they are light years apart, so they don't communicate with each other, but still they have a common feature, that the optical thickness is roughly the same everywhere. So this indicates that there might be some underlying physical mechanism that's causing this feature here. And so that's what we wanted to investigate. And for that, we are using our dust evolution code. So what we are doing here is we see how do dust size distribution evolve in protoplanetary disks. And if I start a simulation now, so you see on the x-axis is the distance from the star. On the y-axis is the particle radius. So we start with small sizes up to 1 micrometer. And we soon grow in the inner disk very, very quickly, because timescales are small in the inner disk. Growth then goes up until this blue dashed line, which is the fragmentation limit. If particles reach these sizes, it basically means their relative velocity is larger than the so-called fragmentation velocity, and rather than they grow to larger sizes, they just fragment down to smaller sizes. And you see that also here, that you replenish small particles as soon as you hit the fragmentation barrier. The green line is the so-called drift barrier. If particles reach that size, their drift speed, so their inward drift speed, is larger than their upward growth speed. So they are basically washed out of the disk quicker than they can grow. So that's the drift limit. And the white line is indicates particles of Stokes number 1, just for reference here. And this is now a smooth disk, but what we need to do is we want to have, well, a pressure trap, so to check what happens if particles are trapped in a bump. And for that, we basically follow the mechanism that also Kees did in his DSHARP paper. If we say in steady state, the gas surface density times the viscosity is a constant. So if we want to have a feature in gas without having to impose like complicated stuff like a planner and so, we can just change the viscosity. And we do it here. So if we want to have a gap in the in the gas, we basically need a bump in the viscosity, and we use the alpha viscosity description. So we just modify our alpha value in the disk, and that should then give us a gap in the gas. And we are using the same function that Kees was using with these parameters. And we have two solar mass star, and we are basically looking at HD 163296 and the outer ring, so ring 2 here, roughly at about 100 AU. And so the only thing that we changed now in our code is alpha. Alpha is now dependent on the location in the disk. So, and if I now run the simulation, it looks like that. You basically see the gas profile roughly in the Stokes number 1 line, because the Stokes number is inversely proportional to the gas surface density, meaning if the gas surface density goes down in the location here where we put our gap, that means the Stokes number grows. That means particles of the same size have a larger Stokes number in the gap, and so the white line just follows the gas surface density profile. And you can also see in the outer edge, we accumulate dust because it has basically a pressure gradient pointing towards the center of this ring in both directions. So we accumulate dust here. And now is the question, what is the surface density, the opacity in this ring? And if we just do that by using the same opacities that the DSHARP collaboration was using, we get to this. So we have opacity, optical depth that is way larger than the observed 0.3 value, and it's even larger than 1. So we are about a factor 7 or 8 larger than the observed value. The observed value and the observed time is here. So that basically means it's too optically thick. We have too much dust in this pressure trap. So that means we need to remove dust. And one idea of removing dust is, okay, we have a dust accumulation. Yeah, that means we form planetesimals in there. So we added a simple toy model prescription for planetesimal formation by whatever mechanism you can imagine. Maybe streaming instability, that is accumulating dust, concentrating dust particles until they can collapse by gravity. And we just use a simple prescription where we say if the dust gas ratio in the midplane is larger than 1, then we trigger streaming instability. And we then remove particles from the dust and put them in the planetesimals by the prescription of Schoneberg, where we can just say, we check how many pebbles are just in the location that we are observing, and we remove a fraction of epsilon per settling time scale. And the settling time scale is given by 1 over Stokes and times omega k. And that means larger particles are just have a larger Stokes number, they are removed more easily. And this epsilon factor, we just took what Choke did in her paper, so we took 10%. And we just implement now this simple prescription into our model, and then it looks like that. So you basically don't see in this plot anything, but if we now look at the optical depth, it changes everything. So you see in the dotted line is the previous simulation without planetesimal formation, and the solid line is now this model where we just remove dust and put it into planetesimals. And you see, basically the disk is for the entire lifetime at the optical depth that we are observing in reality. And why is that? So if I look here now at the dust to gas ratios in purple, so the midplane dust to gas ratio. So our threshold was at 1, a dust to gas ratio of 1. And that's what you see here. There's dust mass accumulated in the ring, but as soon as we hit the dust to gas ratio equals 1 line, then we start to remove dust and put them into planetesimals. And so this line stays now constant because this is a self-regulating effect. If you remove dust particles, you basically stop planetesimal formation until you accumulate enough dust again, and then you start again. So it will stay at this 1 value. And this is also the point where then suddenly the optical depth is not growing anymore because we just removed enough dust mass. And we also looked at the intensity profile, which is a good match. So in the yellow line to the observation, and also the dust ring mass that we have in the end, which is also in good agreement to what Case found in his paper. So to summarize, we put in our dust simulation a dust trap by just having basically a pressure bump in the outer edge of a gap. We introduced self-regulated planetesimal formation, and this might be an indication that there's ongoing planetesimal formation in the disk that we are observing. There can be alternatives. Maybe if you include back reactions, they can smear out concentrations, or scattering effects that what Xiaoman Xu showed can also have an effect in producing these features. If you want to know more about this, I can refer to our paper that we published about this, or you can just hit me up and ask me any questions by email. So thank you for listening to my talk and have a nice day.